we move to Ethernet. Now the CRC is used in every protocol that we know of and is very general, so that's the general. Now we go into Ethernet, and in Ethernet we will talk about actually many different things, and they don't make sense right now anyway, so let me just go on to the Ethernet. First thing Ethernet does is allows multiple access, allows multiple people to talk on one wire. And there are two ways to do multiple people to talk on one wire. One is that you do by time, so everybody has a time limit. You speak sometime, then number 2 speaks sometime, then number 3 speaks, and so on and so forth. This is called time division multiplexing, TDM. Second method is FDM, frequency division multiplexing. That is what is used on cell phones. Somebody is talking on frequency 1, somebody is talking on frequency 2, somebody is talking on frequency 3, and so on. Right? And these are not exclusive. You could do both. You could do time division and frequency division. CSMA-CD. Yeah. Yeah, you could do both. For example, you could do time and frequency. That will be lots of squares here. So for this time, station 1, 2, 3, 4, 5, 8, and the next time, station 8, 9, 10, 11, 12, and so on and so forth. So you could do time and frequency division, and there are other methods of dividing. However, CSMA-CD is what we are doing in Ethernet, and so that was started by a protocol called Aloha at University of Hawaii. You know, in Hawaii, there was the first place that they started wireless networks, and when they started wireless networks, they had basically developed a protocol which was called Aloha for, reason understand. Anybody who has been to Hawaii knows Aloha means hello. Okay? Aloha means hello. So this is a hello protocol. Basically the protocol, the way it works is that you can speak anytime. And that's the hello protocol. Hello is basically you're in a party and you go and you walk up to any person and say hello. You don't need introduction for that. You say hello, I am so and so. And so hello protocol means basically you speak whenever you want. Alright? So that is called multiple access. The problem with that is that if you do math, you will figure out that only 18% of the nodes will succeed, others will collide. So if you go to a party, if everybody says hello at the same time, nobody will know who is saying to whom and what's going on. There will be a lot of collisions. Right? So they said what we will do is we will do a slotted Aloha. A slotted Aloha means that we will put the time limits, and within that time limit whoever speaks, so we will have equal space time, and so in this slot some people will speak, in this slot some other people will speak, and so on and so forth. Okay? So that is slotted Aloha. If you do that, the efficiency goes up by a factor of 2, and that becomes 37%. By the way, it is 1 upon 2e, and this is 1 upon e. Everybody knows what e is, right? The natural log base, whatever. So CSMA means carrier sense multiple access. So the next achievement, extension was that look, please don't speak. Before you speak, listen. Listen before you speak. That means sense the carrier. See if somebody else is speaking. If somebody else is speaking, don't speak. So that is called carrier sense multiple access, CSMA. CSMA means before you speak, you listen for a few microseconds. If nobody is speaking, then you can say hello, or you can send your message in this case. Okay? Good. All right. You waited until I stopped, because if you spoke at the same time when I spoke, that would be called collision. And so that is the next step. The next step actually, before actually that next step was P persistent. P persistent meant that if you find the matter idle, don't speak. If the medium is idle, you take some probability, take a random number P, and then you speak. So if everybody drove a different random number, there won't be any collision, only 1 or 2 people will whoever gets the smallest lower random number will wait actually for that long. So you have to kind of draw a random number how long to wait. And so whoever gets the smallest number will speak up first. And then you don't speak for 1 unit of time and for probability 1 minus b. And the final thing was CSMA-CD. CSMA-CD means that while you are speaking, you listen. And that's what I do. Basically, while I'm speaking, I am actually watching if somebody is trying to speak, and if they speak, I stop. So that is called collision detection. CSMA-CD is carrier sense. Before I speak, I see if nobody is speaking. Multiple access is fine. Basically, that's how we are all trying to share this medium. And CD means if I hear anybody else speak during my transmission, I stop. And in fact, that person will do the same thing. They will stop. In the electronics world, the stations will see if there is any voltage on the wire before they transmit their own voltage or current. Multiple access means multiple people are sharing the wire, right? CD is collision detection, and collision detection means listen while transmitting. So when you are speaking, you see if somebody else is speaking, and then you stop. Same thing happens on the wire. When they transmit, they see they are transmitting 3 volt, but they see 4 volt. Then they know somebody else is transmitting 2, and so they right away stop. So that is called collision detection. Collision detection is listening while speaking. So if it is just MA, multiple access, which means don't listen, MA is called Aloha protocol. Hello. You can just say hello anytime, in any party, any place. And like any party, there will be everybody talking at the same time, and there will be a lot of noise. The efficiency would be 18%. Then you say slotted Aloha means there is a particular time in which you start, the efficiency goes up 37%. Then we say we do this, which is P persistent CSMA, which is that if it is idle, we just don't talk. We flip a coin and decide whether I should talk or not. And then that increases the probability. And then the final one is CSMA-CD, where we do the collision detection. So we'll see the probability one by one slowly later on. We have formulas. But right now, 802.3 CSMA-CD. So everything here is general discussion. But when we went to IEEE, and we started standardizing what we called Ethernet in those days, was put into IEEE 802.3 committee, and so the standard that came out is called 802.3 standard, and that is slightly different from the original Ethernet. The book does not talk about the difference between the two, so I will not talk about the difference between the two. But 802.3 CSMA-CD works as follows. If the medium is idle, then transmits. So that means they don't use P persistence, they use 1 persistent.
What does that mean?
What means is that when you see the medium idle, you just start talking, don't flip a coin. Yeah.
How do you select the P for P persistence?
Well, I mean, the thing is, depending upon the stations, if you have hundreds of stations, thousands of stations, then you use a small P. Basically, you mostly remain idle. And if you have 2 stations, then you select large P. So mostly start talking. Okay? And here we don't know the number of stations, and so we just selected 1 persistent because, I mean, that will cause some collisions, but also it will waste some idle. It will not waste some idle time. So basically, what happened was in those days, we all did. I was in performance analysis group that did the Ethernet performance analysis and all that. So we did the analysis and we said, well, P persistence is okay, but it's not this and that. So we took the best what our analysis showed, simulation, and these are the results. So we went for 1 persistence. And this is 1978. Anyway, the medium is busy, wait until the idle and then transmit immediately. If the medium is busy, wait until idle. So if you go and then you see somebody is transmitting, then you just stay right there, don't leave the place. As soon as they leave, you are ready, right? So wait until idle and then transmit immediately. Another alternative would have been If you go, medium is busy, you go home and then come back 1 hour later. Right? But we didn't select that option. We selected no, you stay right there. If a collision is detected while transmitting, transmit a jam signal for 1 slot. This is interesting. Is that if I am speaking and somebody else speaks, what do? I just said like closely like this. No, you don't do that. You said stop very loudly to the other guy. You please stop. I'm talking. Okay? And the other guy does the same thing to me. He says, you please stop. I'm talking. The reason we have to do this loud voice is because so that it is clear that this voice is not weak. This signal so that the other guy will listen and stop. So that is called a jam signal. Jam signal is a high voltage signal on the wire. High voltage signal. So if you cannot listen to my 0.3 volt, you can listen to my 3 volts. Right? Everybody understand that jam signal? So if you hear anybody talking, then they stop, you stop, they both ask each other to stop. And we say this for 64 byte times, which is 51.2 microseconds. And there is a reason for that too. But anyway, let's right now say that. So we say it for that long so that you are sure to stop. Then after we stop, then we wait for a random time. Now we go home. See, this is the thing. If we collide, then we don't stay right there. Then we say, okay, all right, I think we had a bad day. Let's go home and then reattempt. When to reattempt? Now we draw a random number between 0 and 2 raised to minimum of k 10, 10 minus 1. This is a complicated formula, but there is a reason for that too. But basically k at the attempt. So suppose first time you came, k will be equal to 1. So minimum of 1 and 10 is 1. So you say 2 raised to 1 minus 1 is 1. So we draw a random number between 0 and 1. Random number between 0 and 1. There are only 2 random numbers. These are integer numbers. 0 or 1. Right? With 50% probability you will draw a 0. With 50% probability you will draw a 1. Right? And if you draw a 0, you immediately try again. If you draw a 1, you wait for 1 slot time, which is 51 microseconds. Okay? And then you come back and see if the medium is still idle. The reason is, suppose 2 people are colliding, then one will draw a 0, one will draw a 1, very high likely probability, and then one will continue and the other one will have to wait. Does it make sense? Right? And we assume that suppose 4 people are colliding, then what will happen? 2 people will draw a 0, 2 people will draw a 1, 2 people will start transmitting, they will collide again. Right? If you collide second time, then what we do is 2 comma 10 is 2, so we draw a random number between what numbers? 0 and 3. So you will draw 4 numbers, 0, 1, 2 and 3. 4 numbers, right? If you have uniform distribution means 25% chance that you will draw a 0, 25% chance that you will draw a 1, 25% chance that you will draw a 2, and 25% chance that you will draw a 3. And so whoever draws 0 goes right away, whoever draws 1 has to wait 1 slot time, and so on and so forth. So that will resolve all the cases if there are 4 people involved. What if 8 people are involved? There will be another collision. And if there is another collision, what is the number that you will draw between? 0 and 7. And then 0 and 15, and then 0 and 1023. I mean, all the way up 1023. Once you reach 1023, that is the maximum number of nodes on the network allowed, and therefore we don't go to 2024, I mean 2048 or 47. So at that point, we just take 10 all the time. So at the 11th case, for the 11th collision, we will take what? Same 1023. For the 12th case, same 1023. Right? And we do up to 16 times. If we don't succeed in 16 times, what happens then? We go home forever. Basically, we throw away that packet and try the next one. So this is called, and it is not the word on the slide, I should probably put it, this is called truncated binary backoff. Why it is binary? Because we go by a factor of 2 every time. Why it is truncated? Because after 10, we don't do that, we just truncate at 10. So there are many other possibilities that were tried, simulated, including complete binary backoff, or non-binary backoff, and this was the one that was selected, truncated binary backoff. Collision detected by monitoring, so collision is detected by monitoring the high voltage, 2 or more transmitter, and so on and so forth. Now, the length of the cable is limited to 2 kilometers. That was another decision we had to make as to how long the cable should be, and the question was basically how long we want it to be. So most buildings will be happy with 2 kilometers wire, or most campuses will be happy with 2 kilometers wire, we felt. So we said, okay, local area network we are designing, therefore it should go 2 kilometers, and that's sufficient. And if you think about 2 kilometers, and then you do all that buffer analysis, you have learned how long does it take for the light or signal to go from here to there, how many bits are on the wire. Then you will come to the conclusion that really something like, I think 32 bytes or something like 64 byte is then basically becomes the minimum packet size because of that 2 kilometers. If we would have selected 1 kilometer, we could have been allowed smaller packets. But with 2 kilometers, actually 2.5 to be exact, we could allow up to 64 byte frames. So the minimum packet is 64 byte on 802.3. If you have, let's say, 40 byte packet to send, you send 64 byte. So the 2 kilometer is, okay, in those days the network used to be different. So let me explain what the difference used to be, and then we can come back to these days. In those days we didn't have switches. The network was a segment, segment, a segment, a segment, 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 and then there were repeaters. Something like this. So the 2 kilometers is the maximum distance between any 2 stations, from here to there. Okay, there were no switches. This was just a straight wire, and so there was basically how many bits it will take, time it will take. So basically the key question is, suppose I start transmitting, when will this guy listen to me? When will I have the collision? Right? So that was 2 kilometers. Now the Ethernet is changed. Now we don't have any of that. But we have the switches, and every station goes to the switch. Every laptop is connected to the switch in the closet. And from there we connect to other switches. And we connect to other switches. Right? So here this is 2 kilometers is basically this part. No, sorry. Okay, now there are 2 things. Actually I'm going ahead of me because this is all later on in the class, so I will talk about that later on, but this is different now. Alright, so, and here is the official flow state diagram, if you want to call it that way, for the same thing that I said before. So the way it works is you start with a counter of 0. That means how many times I have tried. I have tried 0 times. So we go and we see, is the medium idle? If the medium is idle, yes, start the transmission. If the medium is not idle, wait 1 slot, and then you see the medium is idle. So you do wait 1 slot, right? And then when the medium becomes idle, you are here and you start the transmission. Now if you collide during the transmission, no, you're done. If you collide, then you send a jam signal, change your counter by 1. Is the counter more than 16? Abort. If it is less than 16, wait for the backoff, draw the random number and all that business, and then you see the medium is idle. All right, let's see a little bit more detail. When this station A starts transmitting, the signal goes both ways from here. Some travels to the left, some travels to the right. These are the electrons, right? And this station starts transmitting, it sees the medium is idle. Even though the station has started talking, this thinks the medium is idle because that current has not arrived here yet. Right? So it starts talking, but after some time it notices that it has collided. This one doesn't even know that it has collided. Is that clear to everybody? What is happening? Because these electrons have not reached there yet. This voltage has not reached there yet, right? This current has not reached there yet. But this current has reached. So this will start a jam signal at this point. And at some point later on, this will start the jam signal too. Now this will have to continue sending that jam signal just to make sure that everybody at the other end of the world can hear it, which is 2 kilometers. Huh?
What do you mean it has to continue to send it? Sends it once?
What, jam?
Yeah.
For 51 microsecond.
Yeah, but it's only stop.
That 51 microsecond is related to the 2 kilometers, yeah.
I'm confused what's happening. Is the data of 2 packets getting like intertwined?
Yeah, right. This is all garbage. Basically, you can't make out any sense because remember that coding thing, we talked about coding. If you are saying that 0 is this volt and minus is this volt and this is volt, all that formula doesn't work anymore.
So that means it's like 2 packets actually colliding and crashing into each other? And
Yeah, the voltage, current, and voltage and current, the waves, the electrical waves are colliding into each other, yeah.
This is half duplex, right?
This is half duplex. That's basically right. Basically, what you're saying is that in the good sense, only packet can go only one way, as opposed to this is half duplex. So yes, Ethernet in the beginning was half duplex. Now Ethernet has become full duplex. So that is another change we can talk about. Although there is not enough time in this class to talk about full duplex, so I won't talk about it. But yes, this is half duplex. Yeah. Yeah, that's the collision. Basically, what is happening is C's signal is going there. It has reached this point up to this point, and A's signal has come all the way here.
Oh, so where's the detection of the collision?
So now C is detect collision at this point. C is going to detect collision at this instant. But A has not detected the collision.
Okay, so C sends the jam signal?
Yes. Now C sends the jam signal and its own bits, these are also traveling. These bits and the jam signal will reach A at this instant. Okay? Now A will send the jam signal. No, yeah, it will be whenever they sense the collision. So that means A will send the jam signal when it senses the collision, which is at this point, not at that point. Is that clear to everybody? That everybody senses the collision at a different time, because there is a finite time when the signal, as the signal travels. Even though it looks like instantaneous, when I am speaking, the voice to that person over there goes few microseconds later than the voice to this person, right? And here we are counting microseconds. No, C will not finish them. C is sending the jam signal for 51 microseconds and it will finish it earlier, yeah. Yeah.
So afterwards he will send the packets, not the jam?
No. After jam, he will have to do the collision algorithm. He has to draw a random number and all that business. When the medium becomes idle. So first of all, C will have to wait because A is transmitting the jam signal. When both have finished transmitting the jam signal, both will draw a random number. Both will flip a coin and then decide who goes first.
They will finish hearing the jam signal before.
Yeah, it will finish hearing, but it is still transmitting its own, right?
Yeah. Oh, so then it's. So it finishes transmitting also before C hears that it finished.
Okay, so it is not allowed. Basically, that's why the packets cannot be so small that you can finish the transmission before you hear the collision. The packets have to be large enough so that you are still transmitting when if you have any collision. So that's why the packets are minimum packet size is 64 byte, and that's a good question. And let me understand let me see if everybody understands that. Why is the minimum packet size 64 byte? Why can't you send 63 bytes? So what will happen is C will be transmitting the jam signal, and it will stop transmitting the jam signal. But the medium is not idle yet because it will still be getting the jam signal from A. Right? When it stops getting jam signal from A, then actually there is a small time difference. I think there is a 9 microsecond or something like that, that you still have to wait to see that the medium is idle, because you cannot just say in one bit that the medium is idle. I mean, it's not really critical. The idea is that when you stop, you have to sense the idle, and sensing the idle means that you have to sense for few microseconds. Okay, and there's a number 96, 9.6 microsecond. You wait for 9.6 microsecond, and then you draw, if the medium is idle, you draw a random number. If it comes out 0, you're lucky, go ahead. If it is 1, then you wait for another 51.2 microsecond. So that is the reason why, because of two things. First of all, the maximum distance was selected first, which was 2.5 kilometer. And if you do 2.5 kilometers, then you will see that the one-way delay is 25.6 microsecond. And so the round-trip delay is 51 microsecond. And the collision window is that's why 51 microsecond. The smallest packet size is 51 microsecond, and so on and so forth, because of all that. They are all related. K is your trial number, attempt is the number. It is 0 on the first attempt, and then you count from there up.
So doesn't that mean that the system is random at all? It's just like
First one you just transmit. So the K equal to 0 means, I mean, you really will not have K equal to 0, because K equal to 0 means that you just transmit as soon as the medium is idle. And if you attempt,
But you do start from 0, K starts from 0.
okay. See, here's the thing. You reset the counter to 0, you're not really using that counter at all. This is K. You're not using it. If you collide, then you increase the counter to 1 and you use the back off. So the formula is never exercised with K equal to 0. The first time you exercise the formula is K equal to 1. Alright, so next thing to know is the address format. So the Ethernet addresses are 48-bit long. All of you know that, right? Because you have seen the Ethernet addresses. They are not decimal numbers, they are hex numbers. Because they are not decimal numbers, we can't put a decimal point between them. We use colon between them. Alright? And so you cannot say this is 80, this is 80. 80 colon 01 colon 43 colon 00 colon 80 colon 0C. Right? They are hex, yeah. So this is also called the MAC address. What does MAC stand for? MAC stands for Media Access Control. This is the MAC. This is the Ethernet MAC. Ethernet Media Address Control. But the real name is 802 MAC Address Control, because all 802 protocols, whether it is token ring, whether it is Ethernet, whether it is Wi-Fi, these are all 802 Cometic protocols. They all use the same address format. In Wi-Fi also we use the same 48-bit addressing. If you look up your computer's Wi-Fi address, which is generally written on the bottom of your computer, it's written like this. Right? Alright. So now, these addresses are 48-bit long. That means we write down 1 byte at a time, 6 bytes, so there are 6 numbers. However, the numbers are, and the numbers are globally unique, in the sense that nobody else will have the same MAC address anywhere in the world. Okay? So you have to go to IEEE and say that I want to make an Ethernet device, so give me some addresses that I can put into my Ethernet device, and so they will give it to you 22 bits at a time. And so you can put those 22 bits, and there are tables on the internet where you can find out, if you see somebody's 22 bits, you know whether it is made by Cisco, whether it is made by, some company, that company. I had a company at some point where we got to IEEE, we got an OUI number, 22 bits. If you see that device, that you know that this was made by Nina Networks. So like that, and basically every company, you can start a company at your home and you can get 22 bits if you want. You have to pay $1,000. You have 2 minutes, 1 minute. Let me finish this slide. And so the idea is you get 22 bits. The first 2 bits are fixed. First 2 bits indicates an individual or a group.
What is individual?
Individual means this is for one computer. Group is a multicast address. Universal or local. Universal means it is unique in the world. Local means it doesn't have that meaning, and then none of these bits have any meaning then. And then 24 bits you assign by the OUI. This is called, this 22 bits are called organizationally unique identifier. This is the company name.